Hi everyone! Today we're going to be running through Dijkstra's algorithm, which is an algorithm that's used to determine the shortest path between any two nodes in a given graph. As our inputs, we have a weighted graph G, a weighted graph meaning that with every edge in the graph, there is a weight associated with it. So for example, if we look at the edge connecting A and B, the weight associated with that edge is 8, which means we have to travel a distance of 8 to go from A to B. And then similarly, to get from B to F, you have to travel a distance of 13. So as our inputs, we have a graph G, and we also have a source node and a target node. In this case, we've chosen our source node to be A and our target node to be H, and we want to find the shortest path from A to H. Now, how do we do this? Well, the first thing you have to do when you run through Dijkstra's is to first initialize table T. And what do I mean by this? Well, table T is going to be a table that contains the distances of every node relative to our source node, and we're going to update these distances as we keep on running through Dijkstra's algorithm. So we'll see an example of how that works in just a second. But the very first thing you want to do is create a row for every node in the graph. So I've created a row for A, B, C, D, all the way until H. And you also want to create columns for those rows. And we'll be updating them as we go along. The next thing we want to do is initialize a list S. List S is going to contain all of the nodes in the graph that we have visited so far. So far, since we visited no nodes, there's nothing in list S, but I'm just going to denote the list by using a curly brace here, and we'll close it at the very end. So let's see. Our source node is A. As far as A is concerned, A's distance to itself is just what? It's just 0, right? A does not have any knowledge of the other nodes in the graph so far. All it has knowledge of is itself. It doesn't know that B is its neighbor, it doesn't know about node D, it doesn't know about node F, etc. So we're just going to set all these distances to infinity to show that A has no knowledge of B or C or D, etc. So we'll just set them all to infinity. Okay, cool. Now we look at our column here and we ask ourselves, which node has the shortest distance from A so far? And the answer to that should be A itself. So now we're going to visit A. We're going to mark the rest of the columns in A's row with an X to denote that A has already been visited, and we're also going to add A to our list S to show that we visited node A. And then now we look at A, and we need to consider who A's neighbors are now to determine the shortest path. So A's neighbors are B, D, and C. So let's look at B first. The distance from A to B is 8. Is 8 better than infinity? Yes. So we're going to update B's distance by writing down 8, and we're also going to denote who updated B with a superscript. So here I'm just going to write A to show that B was updated by A, and its distance has been updated to 8 from infinity. Now let's look at, okay, so we've finished visiting B. Now let's look at C. C is A's neighbor. It can be reached with a distance of 2. Is 2 better than infinity? Yes. So we write down 2, and we write down that A updated C, and now we look at D. D is also A's neighbor. Its distance to A is 5. Is 5 better than infinity? Yes. So we write down 5, and we note that A has updated D using a superscript here. And E, F, G, and H are all not neighbors of A. So we're going to maintain their distance. We're going to keep their distances so far by writing down infinity. And we finished visiting node A. So now what we have to do is we look at our column and we pick whatever node has the shortest distance from A so far. So which of these nodes has the shortest distance? Should be C, right? Because 2 is the least out of every other node's distance that we have so far. So now we're going to look at node C, and we will mark C as visited by adding it to list S. And I shall mark these with an X here. Okay, so let's look at C's neighbors. So now we see that C's neighbors are A, D, and E. But A was already in list S, so we don't have to visit it again because we already visited it during our first run of the algorithm. So we actually don't need to look at A anymore, which is why we have the X's marked here. Let's look at node D instead. D is the neighbor of C. Its distance from C is 2, but we also have to remember to add the distance from A because we're trying to find the shortest. Remember that our goal is to find the shortest distance from A to our target node, and so we need to add we need to be updating the table with the cumulative distance as we go along. So currently our distance from C to A is 2, and when we look at D, D's distance is 2, so we add 2 plus 2, which is 4. Is 4 better than 5? Yes, it is. So we'll write down 4 here, and we're going to mark D as being updated by C. Cool. Now we look at node E, because E is another neighbor of C, and we see that the distance between C and E is 5. So we need to add 5 to 2 because that's going to be the shortest distance, which is the shortest distance from A to E, which is 7. Is 7 better than infinity? Indeed it is. So we're going to update E's distance from the source node to 7, and we're also going to use a superscript to denote that it was updated by node C. Alright. So now we've looked at node D and we looked at node E. So we've visited all the neighbors of C, and so we can keep F, G, and H's current distances from A. And I also forgot to mention we have node B, which we can maintain, whose distance we can also maintain because node B is not a neighbor of C. Alright, so now we have already visited A and C, and we know that because we have X's in the rest of their columns here. So now we have to choose which node has the shortest distance out of all the other nodes. And it looks like it's going to be node D because 4 is the least number out of everything else, least distance out of everything else in this column. So we'll look at node D and we'll mark it as visited by adding it to the list, and we're going to X out the rest of its columns. So who are D's neighbors? Well, we know that D's neighbors are A, C, B, E, F, and G. That's a lot of neighbors, but the good thing is we don't have to check all of them because we've already seen A and C. So really, we only have to check B, F, G, and E. We always need to update the table with the cumulative distances rather than just the distance between D and its neighbors. So let's take a look at the distance from D to B. The distance from D to B is 2, and we know that the shortest distance from D to A is 4. So 4 plus 2 is 6. Is 6 better than 8? Yes, it is. So we're going to update B's distance to 6, and we're also going to use the superscript to denote that it's been updated by node D. Now let's look at node E. Is E a neighbor of D? Indeed it is, and their distance between D and E is 1. The current shortest distance recorded in the graph from our source node to E is 7. But now that we're looking at node D, we know that the shortest distance from A to D is 4, and the distance from D to E is 1. So we do 4 plus 1, which is 5. Is 5 better than 7? Yes, it is. So we're going to update E's distance to 5, and we're going to use a superscript to denote that it's been updated by D. Now let's look at F. F is also a neighbor of D, and the distance between D and F is 6. 6 plus 4 is 10. Is 10 better than infinity? Yes, it is. So we're going to update F's distance to 10, and we're going to use a superscript to denote that's been updated by D. Now let's look at G. G's distance from D is 3. 3 plus 4 is 7. Is 7 better than infinity? Yes, it is. So we're going to update G's distance to be 7, and we're going to use a superscript. And now finally, H is not a neighbor of D, so we're going to keep its distance at infinity. We're finished visiting node D. All right, so out of all the nodes in this column, which one has the shortest distance from A? That's going to be node E, and node E has not been visited yet. So we're going to add node E to our list S, and we're going to X out all the other columns of E. Great. So now E is over here. We know the shortest distance recorded so far from A to E is 5. Now let's look at E's neighbors. E's neighbors are C, D, and G, but we already visited C and D, so we don't have to worry about these two guys. We need to worry about G. So G's current distance from A is 7, but we know that the distance between E and G is 1. What is 1 plus 5? 6. Is 6 better than 7? Yes, it is. So we're going to update G's distance from A to be 6, and we're going to say the guy that updated G is E. So we're going to update the superscript, and all right. And then that looks like, so we were on node E, and we've already visited all of E's neighbors, so we can keep the distances of all the other nodes in the graph, in the table, sorry. And yeah, E was visited. So out of all the nodes in this column here, which one has the shortest distance? Well, it looks like we have a special case because G and B have the same distance from A. So it doesn't actually matter which one we choose first. I could choose to visit B first, or I could choose to visit G first. In this case, I'll just go in order, so I'll visit B. So I'm going to add B to our list S, and I'm going to X out the rest of its columns. Now let's look at B. And who are B's neighbors? B's neighbors are A, D, and F. But we've already visited A and D, so we only have to look at F. The distance between B and F is 13, and the current shortest distance from A to B is 6. So to get from A to F, we have to add 6 plus 13, which is 19. Is 19 better than 10? No, it is not. So we keep 10. We do not update F's distance from A because 19 is greater than 10. Now let's look at G. G is not a neighbor of B, so we're going to keep G's distance. And H is also not a neighbor of B. It's all the way over here, so we're going to keep its distance at infinity. Now, which of these nodes in this column has the shortest distance from A? Looks like it's G here. So let's add G to our list S, and let's check out who G's neighbors are. So it looks like they're going to be D, E, F, and H. But we've already visited D and E, so we only care about F and H. So before we jump into analyzing the distances of F and H, let's first do the X thing again to make sure that, to mark that G has been visited. And okay, now let's look at F and H. So the distance between G and F is 2, and the current recorded shortest distance between A and G is 6. 6 plus 2 is 8, meaning that our new updated distance from our source node A to F would be 8. Is 8 better than 10? Yes, it is. So we're going to update F's distance, and we're going to say F got updated by G. Great. Now let's look at H. The distance between G and H is 6. And the current known shortest distance from A to G is 6. 6 plus 6 is 12. Is 12 better than infinity? Yes, it is. So we're going to mark H's distance to be 12, and we're going to say it was updated by node G. Awesome! So we've finished visiting G. Now, what is the shortest distance node from A out of F and H? Well, it looks like it's going to be F, right? So we're going to mark an X to say that F has been visited. We're going to add F to our list S. And let's look at who F's neighbors are. F's neighbors are B, D, G, and H, but we already visited B, D, and G, so we only care about H. F's distance to H is 3, and F's shortest distance so far from node A is 8. So 8 plus 3 is 11, and is 11 better than 12? Well, yes it is. So we're going to mark H's distance from A to be 11 now, and we're going to say H got updated by node F. And finally, we only have one more node left in this last column, and that's node H, so we're going to mark H as visited, and we've finished populating our list S. But be careful, because list S is not the actual shortest path from A to H. This is not the shortest path, and I want to really, really emphasize that because a lot of students get confused. The actual way to construct the shortest path is to work backwards from your target node back to your source node. So let's look at our target node, which is H. We need to ask ourselves, who updated H? F updated H. So we're going to draw an arrow, and we're going to arrow pointing left because this is going to be our path, and we're going to write down F. Now let's ask ourselves, who updated F? Let's go back to F and look at the superscript. It looks like G updated F. So let's mark another arrow and mark down G. Who updated G? E updated G. So we need to mark another arrow, put down E. Who updated E? D updated D. So we write down D. Who updated D? C updated D. Write down C. Now who updated C? A updated C. And look, we're back at our source node, A. And our destination node was H. So from looking at who updated who based on list S, we can construct the shortest path from A to H, which is going to be A, C, D, E, G, F, and H. This is going to be our shortest path. And if you add it up together, it'll be 2 plus 2 plus 1 plus 1 plus 2 plus 3. And that gives us a total distance of 11. And that looks pretty reasonable, given all these possible paths that we can take from A to H. So yeah, Dijkstra's algorithm can be really, really cool when applied. You'll learn about how to implement Dijkstra's algorithm using different kinds of data structures, which is a little beyond the scope of this class. For now, you just have to know how to run through the algorithm using this table T and list S. But this is our final shortest path from A to H. And hopefully that gives you a clearer idea as to how this algorithm works. We won't be proving why this algorithm works in this class, but if you're interested, we would highly recommend that you take analysis of algorithms at some point. I hope you guys found this video helpful, and let us know if you have any other questions.